Now, what about the numerical method of solving this problem? Okay, let's erase this one. Okay, so okay, let's come here first in our graph. As we remember in our calculus class, the derivative of our function is actually the slope of our function. If you take the derivative of our function at that point, then that is equal to the slope of our function at that point. So that would mean, let's say we'll have this one. Okay. Right. So let's say at this point, the derivative of our function as it at this point is equal to this slope. Okay. Now in our numerical method, we approximate. So how do we approximate this slope? Or that is, how do we approximate the derivative of our function? Well, we can have this point and this point, connect these two, and that would be okay, so that's it. Okay. This will now be our, let's say, let's have these two tentative points, arbitrary points, sorry. Now this will be our t at I. This will be our t at I plus 1. This will be our corresponding v at time I. And this is our v at time I plus 1. That means we can have this one as our delta v, then this one as our delta t. So we have approximated this slope by this slope, the blue slope, the blue line. Now, as we can, this is just to illustrate graphically, as we can remember in our calculus, dv dt is equal to the limit of delta t as it approaches to 0 of our delta v delta t. That is, as this point, this delta t, as our delta t approaches to 0, okay? As this approaches to 0, this slope will approximately become equal to the slope of this line. Therefore, we can actually approximate delta v dv dt as delta v over delta t. And since our delta v, our dv dt is equal to this expression with v at that particular moment, so that will be it's approximately equal to vi plus 1 is vi over and then let's rearrange, because our goal here would be to come up with an expression of our velocity. Okay, maybe it will be clearer as I finish. Okay, so I just rearrange terms. By this you can see that if we have the initial value of our v at time I, then we can determine the velocity at a later time I plus 1 just by having this, okay, the initial values. So let's say at first iteration, let's say, so that would be we are going to use ti equal to 0. Then this will be t 0 plus 1, so that is t at 1. Then v0, so we can have v1. Then v1, we can then use v1 for v2. That is for the next iteration. Okay, let's illustrate. Okay, let's just analytical method, numerical method. Okay. Still, we know that at the initial velocity at time equal to 0, your initial velocity is 0. So we can still take this one. Now, this initial value, we can use that for our first iteration. That is from time 0. As you can observe here, in our analytical method, we use a time step of 2 seconds. So let's be consistent. Let's have that one. Let's determine now the velocity at after 2 seconds. That is from 0 to 2 seconds. Then we'll have v at, how should I say this? It's from v0, then we now go to v1. Then from v1 we again go to v2 and so forth. And just like this. So this will be v0 plus 1 equal to v at 0 plus, okay, so let's have v1. That would be it's g is 9.81, 9.8, 12.5, 68.1. V at 0 is 0. Then, oops. At I equal to 0. Okay. So V at I equal to 0. This is 0. Then this is at 2 minus 0. We'll have V this is 19.6 meter per second. And then, so at our first iteration, we'll have V1 at 19.6. Now, let's have another step size of 2 seconds. That is now from 2 to 4. Then we can have our V2. That then the previous value, that's 19.6 plus this will be equal to 32 meter per second. 32 meters per second, that's our V2. This is our velocity, our approximate velocity at time equal to 4 seconds. This will be our approximate velocity at time equal to 2 seconds. So, at time equal to 6, you just have to do this again. Then at time equal to 8, we'll use the value at time equal to 6, and so forth. Okay. Now, the table of values for that would be okay. So as you continue this computation, eventually you will also end up with this value, 53.39. Now let's try to graph that. That would be at 2 it's 19.6. It's here. 15, 17 over here. At 4 it's 32. It's 32. That's 5, so here. At 6 it's 39. It's here. At 8 it's 44. It's here. At 10 it's 47. It's 47, so it's here. At 12 it's 49. It's about here. So that would be, let's use another color. Okay. So this is how the numerical method approximates the analytical, the values for our analytical method. Now, you might think that the analytical method is easier, but it's easier if the problem involves only instances like this. However, when for more complicated problems, numerical methods will give us will save us from headache. Then, if you can, let's also consider that this will be done by our computers, and as you can see, as what I said earlier, numerical methods, it's a set of procedures done to approximate the solution to our equation. Then it's done iteratively, in which we reduce we reduce the expression. Just we have, what's our expression last time? It's, we have had VT got to 53.39 1 minus E so we have reduced this expression to simple mathematical operations. Just addition, subtraction, then division, and multiplication. Operations which our computers can do. And because our computers can do it very fast, then we can have the approximate solution in a quicker way, such that for complicated problems, we need not to go through the hard math. Okay, so I think that's. Should there be anything else? I think that's all. That's all for this topic. Okay. So thank you for watching. And if ever you have any questions, you can just PM me or in our Google Classroom. Now there's one thing that I forgot to mention. As you can observe in the graph, or even in the tabulated values, there's quite a big difference between the values of our analytical method and our numerical method. And you can also see it here, the graph of our velocity. Now, if you want to be more accurate in our numerical method, what we can do actually is for this one. That is, we need to take a smaller time interval. In this case, we took 2 seconds for every time interval. But if we will be, let's take 1 second. So these values will be closer to this one. This is the true value. This is our approximate value. And if we take shorter time interval, then we will have more accurate values. But the trade-off with that is there's a longer computational time. So yes, it will be more accurate, but it will take us a longer time to arrive at the solution, at the answer, at an acceptable answer. So basically, in numerical methods, that we always have that trade-off. Just have to the trade-off between accuracy and computational time.